Hey guys, Mr. Backerberg here. In this video, we're going to look at complex conjugate zeros. So suppose we're dealing with some polynomial function f of x, where our function has all real coefficients. If we have the imaginary zero a plus bi for our function, then its conjugate a minus bi will also be a zero of our function f of x. So complex zeros always show up in pairs, and they are always complex conjugate pairs. So a plus bi and a minus bi. So let's say we wanted to find a polynomial given some zeros. So we are given zeros of -3, 4, and 2 minus I. So if we're trying to build this polynomial function, then we want to think about the factors that would give us these zeros. So if we're looking at the -3 first, then the factor that would give us -3 as an answer would be x plus 3. And if we're thinking about the 4 as a 0, then the factor there would be x minus 4. Now here, because we have 2 minus I, that's an imaginary zero, we just said that if we have an imaginary zero, then its conjugate also has to be an imaginary zero. So if we have 2 minus I, then we also need to add 2 plus I to our list of zeros. Now as far as thinking about the factors for these imaginary zeros, it might be a little tricky to think about, but I'm going to refer to the 4. When we had 4 as a 0, we went x minus 4. So in here, when we have 2 minus I as a 0, then its factor is going to be x minus the 0, which is 2 minus I. And I'm going to do the same thing with my conjugate 0 in there, so x minus, and then I'm going to throw in the 2 plus I. Now when we FOIL out the first set of factors there, we should end up getting x squared minus x minus 12. Now multiplying the second set of factors might be a little bit trickier. So what I'm going to do first in here is I'm going to take this negative and actually distribute it into that set of parentheses. So then this first factor is going to look like x minus 2 plus I. And if I distribute the negative through my second factor's parentheses, then that's going to leave me with x minus 2 minus I. And now what I'm going to do is work on multiplying these together by doing a whole bunch of distributive property. So x times x is going to get me x squared. X times -2 is -2x. And x times -I is -ix. Then I'm going to distribute my -2, so -2 times x is -2x. -2 times -2 is plus 4, and -2 times -I gives me plus 2i. And then I need to distribute my I, so I times x is plus ix. I times -2 is -2i, and I times -I is -I squared. Now I'm going to look at that second set of parentheses because there's going to be some cleanup work that we can do in there. And the first thing I'm going to do is look for things that are going to cancel each other out. So I'm looking at the negative ix and the positive ix in there. Those will cancel each other out. I see a plus 2i and a minus 2i. Those will cancel each other out. That takes care of everything that's going to cancel out, but if we look at combining some like terms in there as well, we'll have the x squared. If we look at -2x and -2x, that's -4x. Now on the back end, we've got this I squared. Remember, I squared is really the same as -1. So if I combine the plus 4 in here with the minus -1, double negative is going to turn this positive, so that's going to turn into a plus 5 on the end. But I'm not quite done because I've still got more distributive property to do. So I'm going to start by distributing this x squared. So x squared times x squared gives me x to the 4th. X squared times -4x is -4x cubed. And x squared times this plus 5 on the end is plus 5x squared. Then if I take the negative x and distribute it to the x squared, I'm going to get -x cubed. Negative x times -4x is positive 4x squared, and negative x times the plus 5 on the end is going to give me minus 5x. And then I need to distribute my -12 as well, so -12 times x squared is -12x squared. -12 times -4x gives me plus 48x. And if I take the -12 times the positive 5, I will get minus 60 on the back end. Now I need to combine like terms one more time. So I see the x to the fourth. Then if I look at my x cubes, I've got negative 4x cubed and negative x cubed. So that's going to give me negative 5x cubed. Then if I look at my x squareds, here I've got 5x squared plus 4x squared minus 12x squared. So if I combine all of those, I should get negative 3x squared. As far as my plain x's, I've got this negative 5x and this plus 48x. So it should give me plus 43x. And then I've got my lone minus 60 on the back end. So this polynomial is our function that would give us all of those zeros that we started with initially. In this example, we're going to look at the function f of x equals x to the fifth minus 3x to the fourth minus 5x cubed plus 5x squared minus 6x plus 8. And what we're going to do is look at factoring out this polynomial all the way. And in order to help us, we want to actually look at what some of the zeros are, and we're going to find those things graphically. And then once we find some of those zeros, then we're going to start running synthetic division to help us find some factors. So in my calculator, I've already got my function typed in. So when I hit graph, as we're looking at the graph, when we're looking at zeros or x-intercepts, I can see that my graph is crossing at around negative 2, at 1, and also at 4. So because we have zeros at x equals negative 2, x equals 1, and x equals 4, we can start to get our polynomial factored out. For the 0 of x equals negative 2, that factor would be x plus 2. For the 0 at 1, that would be the factor x minus 1. And for the 0 at 4, that factor would be x minus 4. But we don't know what the other factors of our polynomial are going to look like yet. So what I'm going to do is run through and do some synthetic division with these zeros that we've got to try to figure out what would be left in our polynomial as we're breaking it down into these different factors. So I'm going to start doing synthetic division, and I'm going to start with the negative 2. So we drop down the 1. 1 times negative 2 is negative 2. Add these together, we get negative 5. Times negative 2 gives me positive 10. Add these together, we get 5. Negative 2 times 5 is negative 10. Add those together, we get negative 5. Times 2 is positive 10. Add these together, and we'll get 4. And 4 times negative 2 is negative 8. So we get 0. Which confirms that negative 2 is a 0 of our function. Then from there, I'm going to keep going with what I've got, except this time I'm going to do synthetic division using the 1. So I'll drop down the 1. 1 times 1 is 1. Add these together, we'll get negative 4. Multiply, and we'll still get negative 4. Add those up, we'll get 1. 1 times 1 is 1. Add those together, we get negative 4. And 1 times negative 4 is negative 4. So we get a 0 remainder, confirming that 1 is in fact a 0 of our function. And then I'm going to do synthetic division one more time, and I've got my 4. So I'm going to drop down the 1. 1 times 4 is 4, so I get 0 there. 4 times 0 is 0. Add those up, I'll get 1, and 1 times 4 is 4. And add those up, and we get 0 again. Now, these 1s and 0s in here, what I'm going to do is take those and rewrite those in polynomial form, so with the variables back in there. Now, we started with a 5th powered function, but we did 3 rounds of synthetic division, so we would have to drop the power by 3. So this 1 is really on an x squared, this 0 is on a plain x, and this 1 is our constant on the back end. And if we get rid of that 0x in the middle, then that tells us that our remaining factor is really x squared plus 1. But if we're thinking about what the factors of our polynomial are, then I would actually want to think about this x squared plus 1 and do a little solving with it. So I'm going to set it equal to 0, and I would have to subtract that 1 over to the other side, so I would get x squared equals negative 1, and I would square root both sides. So I would get x equals. Now when I do this square rooting, I have to remember to put a plus and a minus in there. And when I square root -1, I get I. So I've really got extra zeros happening at x equals I and at x equals -I. So I can rewrite those, thinking about those as factors. So we would have x minus I, and we would have x plus I to add on our list of factors with those other ones that we had earlier. So the complete list of factors for this quintic polynomial are x plus 2, x minus 1, x minus 4, x minus I, and x plus I. So in this example, we're going to show that 1 minus 2i is a factor of f of x equals 4x to the fourth plus 17x squared plus 14x plus 65. And then we'll want to find the remaining zeros and write out our function in its linear factorization. So we're going to do some synthetic division in here. As I start writing this out, notice that we're missing the x cubed term, so I'm going to fill in a 0 there for the x cubed. Now when we do our synthetic division, we're going to use the 1 minus 2i. So this will look a little bit different than the synthetic division that you're used to doing, but we're going to start out the same. Drop down the 4. 4 times 1 minus 2i, we would have to distribute the 4, so we would get 4 minus 8i. And when we add these together, 0 plus 4 minus 8i is 4 minus 8i. Now doing this multiplication in here might get a little tricky. Trying to multiply 4 minus 8i times 1 minus 2i. And we can actually use our calculator to help us out with multiplying these imaginary numbers together. On your calculator, the I button is directly above the decimal point. So if I wanted to do 1 minus 2i and multiply that by 4 minus 8i, then when I do that, I can see that I get -12 minus 16i. Now here, when I add the 17 with the -12 minus 16i, the 17 is a real number, so I'm going to combine that with the -12 on the front, since that's the real number. So I would be left with 5 minus 16i. When I take the 5 minus 16i times the 1 minus 2i, I'm going to get -27 minus 26i. Adding these together, that's going to give me -13 minus 26i. And when I take that and multiply by my 1 minus 2i, I'm going to get -65. So then we add those together and we will get 0 at the end. So that does in fact confirm that we have a 0 at 1 minus 2i. Now since we have an imaginary 0 at 1 minus 2i, then its conjugate also has to be a 0. So we're going to have a 0 at x equals 1 plus 2i. And I'm actually going to do the synthetic division to confirm that, because then we're going to be able to look at what's left over to figure out what the rest of our zeros should look like. So I'm going to start by dropping down the 4. 4 times 1 plus 2i gives me 4 plus 8i. When I add these together, the -8i and the +8i are going to cancel each other out, but the 4 plus 4 gives me 8. 8 times 1 plus 2i gives me 8 plus 16i. When I add these together, the -16i and the +16i cancel each other out, but the 5 plus the 8 is 13. 13 times 1 plus 2i gives me 13 plus 26i. And I can see that the 13s and the 26i's are going to cancel each other out in there, leaving me with 0 as a remainder. Now if I put the x's back into what's left over, I started with a fourth powered function, but I did 2 rounds of synthetic division, so I would have to drop the power by 2. So this is going to leave me with 4x squared plus 8x plus 13. Now to find the rest of my zeros in here, I'm going to do the quadratic formula. So I've got my a, b, and c values plugged in there, but I can simplify this down. Now as I'm looking at this simplified down version, we've got that square root of -144. Now 144 is nicely square rootable, and since this is negative, we're going to end up with an I in there. So we have -8 plus or minus 12i all over 8. Now I can think about simplifying this down a little bit further. -8 divided by 8 is -1. and I've still got my plus and minus in there. But if I take the 12I divided by 8, I'm going to be able to reduce down that fraction to being 3/2 I. So as far as my other zeros, I'm going to have a 0 at x equals -1 plus 3/2 I, and I'm also going to have a 0 at x equals -1 minus 3/2 I. Now if I want to think about writing out the factors for all of these zeros, if I look at that first one, x equals 1 minus 2i, that would be x minus the 1 minus 2i. And I'm going to write out all of my imaginary zeros that way. But there is one more thing that I need to put in here. If we think about our original function, we had a leading coefficient of 4. So I need to account for that leading coefficient in here. So in front of all of these linear factors, I'm going to sneak that 4 in there. So this would be the linear factorization of that quartic polynomial function with all imaginary zeros. That's going to be it for this video. Thanks for watching.